Hello everyone, and welcome back to our channel where we dive deep into the science behind the headlines. Today we're tackling a topic that is both terrifying and fascinating: tsunamis. Specifically, we're going to break down what it means when officials say a tsunami threat is being assessed, and that potentially hazardous waves are expected. What really happens behind the scenes during those crucial first moments after a major undersea event? It all starts with a trigger. The most common cause of a tsunami is a powerful undersea earthquake, but they can also be generated by volcanic eruptions, landslides, or even meteorite impacts. Let's focus on earthquakes. When tectonic plates shift abruptly beneath the ocean, a massive amount of energy is released, displacing a huge volume of water. This isn't like a normal wind-driven wave that just affects the surface. This is the entire column of water, from the seafloor to the surface, being lifted and then dropped. This initial displacement is what sets the tsunami in motion. Immediately following a significant earthquake, a global network of seismic sensors springs into action. These sensors detect the earthquake's magnitude, depth, and location. This is the first piece of the puzzle. Tsunami warning centers like the Pacific Tsunami Warning Center in Hawaii or the National Tsunami Warning Center in Alaska receive this data within minutes. Their first job is to determine if the earthquake has the potential to generate a tsunami. Generally, an earthquake needs to be at least a magnitude 6.5, and it must be a shallow quake occurring under the ocean floor, causing vertical displacement of the seafloor. If these criteria are met, the first level of alert is often issued, a tsunami watch or a tsunami information statement. This is the assessing the threat phase. It means, we have a potential situation here, and we are gathering more data. This is where the DART system comes in. DART stands for Deep Ocean Assessment and Reporting of Tsunamis. It's an incredible network of buoys strategically placed in the deep ocean. Each DART station consists of two parts: a bottom pressure recorder anchored to the seafloor, and a companion buoy on the surface. The seafloor unit constantly measures the pressure of the water column above it. When a tsunami wave passes over, even if it's just a few centimeters high in the deep ocean, the pressure recorder detects this change. It's so sensitive it can detect sea level changes of less than a millimeter. This data is then converted into an acoustic signal and sent up to the surface buoy. The buoy transmits the information via satellite to the tsunami warning centers in real time. This is the moment of confirmation. The seismic data told us a tsunami could happen. The DART buoy data tells us a tsunami has been generated. This is a critical distinction. It allows scientists to confirm the existence of the tsunami and to begin refining their predictions about its size and arrival time. Without the DART buoys, we would be relying solely on models, which are good, but not as reliable as direct observation. With confirmed data from the DART buoys, scientists turn to sophisticated computer models. These models are incredibly complex. They take into account the initial earthquake data, the DART buoy readings, and detailed maps of the ocean floor, known as bathymetry. The shape of the seafloor plays a huge role in how a tsunami travels and how it will behave when it reaches a coastline. Underwater mountains, ridges, and canyons can focus or disperse the tsunami's energy, much like a lens focuses light. The models run thousands of simulations to forecast the tsunami's path, the wave arrival times for different coastal locations, and, most importantly, the potential wave height. This is when the alert level might be upgraded from a watch to a warning. And you hear that phrase, potentially hazardous waves are expected. So what does potentially hazardous actually mean? In the deep ocean, a tsunami might be barely noticeable, traveling at the speed of a jetliner over 800 kilometers per hour, but with a wave height of maybe less than a meter. The danger begins as the tsunami approaches the coast. As the water becomes shallower, the front of the wave slows down, but the energy and water behind it continue to push forward. This causes the water to pile up dramatically, a process called wave shoaling. A wave that was only a meter high in the deep ocean can grow into a monstrous wall of water, 10, 20, or even 30 meters high upon reaching the shore. This is why even a forecast of a 1-meter tsunami can be extremely dangerous. It's not a 1-meter increase in the normal tide level. It's a surge of water, a powerful, fast-moving current that can rush inland for hundreds of meters or even kilometers, carrying incredible force and debris. It can sweep away buildings, cars, and infrastructure with ease. The term hazardous waves also refers to the fact that a tsunami is not a single wave, but a series of waves, often called a wave train. The first wave is not always the largest, and dangerous waves can continue to arrive for hours after the first one. That's why it's crucial to stay away from the coast until the all clear is given by officials. Once a tsunami warning is issued, the information is broadcast through every channel imaginable. Emergency alert systems on phones, TV and radio broadcasts, and local sirens in coastal communities. This triggers evacuation plans. Authorities will direct people to move to higher ground away from designated inundation zones. The accuracy of the scientific assessment and modeling is literally a matter of life and death, as it determines how much time people have to get to safety. So, to recap the entire process, an undersea earthquake triggers seismic alerts. Tsunami centers assess the quake's potential. DART buoys in the deep ocean provide real physical confirmation that a tsunami has been generated. Sophisticated computer models then forecast the tsunami's path, arrival time, and potential size at the coast. This leads to the issuance of watches and warnings, communicating that potentially hazardous waves are expected. It's a remarkable combination of geology, physics, engineering, and communication, all working together in a race against time to save lives. Understanding this science helps us appreciate the warnings and know exactly what actions to take to stay safe. Thank you so much for joining me today to explore the science behind tsunami warnings. I hope you found it informative. If you did, please give this video a thumbs up, and don't forget to subscribe and hit that notification bell so you won't miss our next scientific deep dive. Stay curious and stay safe.